All right, so now we're going to talk about PCA, which is section 37, right? So I think you guys all said feeling pretty good about it and stuff like this. In general, like I've actually heard this PCA talked about as one of like the hardest concepts in machine learning. I don't know if I actually agree with that, but maybe that's just me. Maybe it's just something that kind of clicks well for me personally. But PCA and dimensionalities will be really important for a lot of different, like, how do I say this? PCAs usually can be used, they got thought of as an algorithm for itself. It's kind of like the first unsupervised learning algorithm we're really talking about. But you can also think of it as like a pre-processing step. Basically can really help any kind of project going forward. Okay. So before we dive into PCA though, I do want to talk about dimensionality. So oops, let's minimize, there we go. Okay. So well, the reason why I want to kind of discuss this, and I think the curriculum kind of mentions this a little bit, is that there's kind of this this idea called like dimensions. So real quick, before we kind of dive into dimensionality and like what this means and how it relates to PCA, can someone describe to me like what is a dimension? Like how would you say, when I say, oh, it has high number of dimensions, what do we mean by that in this terms of data science?
I think of it like it's on many different planes for our graph. So tons of different, I don't know.
That's good. So different planes, like kind of, you can adjust it on different parts. You can think of like a different axis, right? So like you can travel along this direction or like, this plane or this plane, right? And kind of adjust on those parts. Any else want to kind of add in a little bit to what they think of as a dimension?
Yeah, it's like a variable or a feature. It's just that you're thinking of it in spatial terms. Like instead of just saying, oh, this elephant weighs this much and the other one weighs another amount, you're putting that into a Cartesian plane or a space, which is great because then you can have multiple dimensions that you wouldn't normally relate to one another and just treat them with different dimensions in this space.
Yeah, good. So you can really think of like dimension data science like as features. That's kind of really what they are. You can think of them like, if you think of them in a data frame, they're like columns. Like that's really what I mean. Like every column is a new dimension essentially. I'd like to think of them as kind of like scaling, like a little scale where we can like adjust the slider on like kind of like this feature, like, especially continuous variables, but like, going forward, like, oh, this is more and more of, I don't know, let's say brightness or something. It's like, oh, increase the brightness in this direction. It's like, oh, but I can also increase or decrease like the contrast, right? Like those would be different dimensions, but those are both features. So really when we say dimensions, you can think of features or columns. You can also think of like categories as dimensions as well. In this case, we usually think of it like hot encoding, since basically you can't say like, we can't turn like a slider to be like more red, blue. You can technically try to do that by converting into numbers, but you can think of it more like, oh, is it red? Yes or no. Is it blue? Yes or no. Is it, an elephant? Yes or no. So in that case, that scalar is basically just a 0 or 1, kind of like you go all the way to the left, all the way to the right. Okay, so that's why I kind of want to talk about dimension. So looking at dimensionality and stuff like this, it actually turns out to be one thing PCA is really useful for is reducing dimensions. And basically the idea here is that we have something called the cursive dimensionality, which the curriculum kind of goes into a little bit, but I want to reemphasize it a little bit here. Is the cursive dimensionality kind of says a little bit, basically, it's kind of like the opposite of what we want with the kernel trick, if you remember back from support vector machines. But basically, as you have more dimensions, things become more spread out, or your data points become more spread out, become more sparse is what we usually call it. And it's kind of these weird, interesting things that I think kind of like, it's hard to grasp a little bit. But like one example of this, and I'm going to try to do this very quickly without getting into too much detail, but it's a really interesting problem. Basically, you start off with 2 dimensions. You say, okay, let me get like a 1 by 1 square. And so let me go ahead and put a circle that touches tangentially on each side. Okay. And then say, okay, let me go ahead, after you do that, let me go ahead and put 4 circles that touch the circle in the square, like on the edge like this. And you say, okay, how big are basically these circles compared to the square? And obviously they're smaller, right? There's some percentage or whatever, right? And so you can figure that out. And then you can say, okay, let me try to do the same thing with 3 dimensions, where essentially we get a cube, like a 1 by 1 by 1 cube, and you put like essentially like a big ball in there where the ball will fit or touch just, and I'm not going to be the best drawer here, but like will touch each of the edges. Essentially, it's like as big of a ball you can put in there in a single box, right? And then you say, okay, how big of like, you know, these kind of like smaller balls, like in the corners, essentially, where they touch basically the ball in the box. Say, oh, how big are these balls? And it turns out, if you actually kind of think about, like if you can mentally think about this, it turns out that these little balls that are in these corners, percentage-wise, they're actually bigger compared to these ones to the radius. So like if you imagine this is like unit 1 right here, and this is like a unit 1, this ball's radius will be bigger than this circle's radius. Okay, so it seems like, oh, as you kind of like, you know, increase in 3 dimensions, the balls can get slightly bigger. And because of mathematics, we can't really visualize this, but you can basically extend this out to 4 and 5 and 6 and 7 dimensions. And it turns out as you go into higher and higher dimensions, this ball will continue to get larger and larger and larger. In fact, I can't remember what dimension, I think it's dimension 6 or 7. But after that point, the balls that are in here that would be on this like corner that be touching just this little part actually end up having more volume than the actual cube. And it's a volume like hyper volume. So basically they're actually bigger than the actual cube. They actually kind of end up being like a lot more spread out. And it's kind of this weird unintuitive part because obviously we can't picture what a 7th dimensional ball looks like. But what's kind of cool about this is, oh, sorry, I think my thing got disconnected. You guys still hear me okay? Okay, so, excuse me. As these balls, I'm sorry, as we get in higher and higher dimensions, basically it means that there's more space for this ball to expand outward. And that's essentially what the curse of dimensionality really says. Okay. So I kind of want to say that a little bit, like it's an unintuitive thing, but it relates really well to like why essentially when we get higher and higher dimensions, essentially it's harder and harder to like relate things. We need more and more data points to fill in those dimensions, which is kind of a big deal since, you know, sometimes we're dealing with certain data sets that have like 100 different features. And that means basically your 100-dimensional data set. Also think of like one-hot encoding. If you have like, you know, 5 features, but one of those features categories, and those categories can be 10 different categories, you now have 10 additional features. So you can imagine now your data gets a lot more sparse, and basically it's a lot harder to relate the two together. And this is actually going to be really important in unsupervised learning where we do clustering. Okay. So I'm kind of seeing about how we would kind of reduce those dimensions. It's kind of nice to kind of say, okay, let's think about data points that are on like on a 2-dimensional plane and see, can we reduce this? So in this case, you can see like there's more or less random data points, right? I just kind of coded this up real quickly. What kind of, like, how many dimensions do we need to really explain each of these data points? And this sounds like a really intimidating question. And it's really saying like, you know, how many numbers do we need to describe this one data point? 2. Yeah, see, Andy said 2. Basically, you need an x coordinate, right, and a y coordinate. So it means that this data set overall is 2-dimensional, right? We need 2 dimensions. We need 2 features to really describe this data set. There's no shortcut really we can do, okay? So this kind of brings us into our next point. It's like, okay, this one's like, let's say we have a line that's along the y-axis. Okay, so here we can say like all the points are on the same y. How many numbers do we really need to describe this data set? Now, I know technically we can do it with 2, right? And I think I saw you guys go right away. You guys know what I'm going towards, 1, right? And basically it's because like, oh, we can say, well, all right, no, like you tell the person, know that every number that I'm going to tell you is just on the same y equals 1. And then just give them the number of where they are in the x dimension. So you can really say this line right here in the y dimension is 1-dimensional. Essentially, you can describe everything with essentially just using the x point, as long as you know what the y is, right? Okay. Makes sense so far, right? And then, so this one comes a little bit hard, like not harder, but like a little different. So now we have a straight line, but it's diagonal. How many dimensions would we say this is? How many real numbers would we need to describe this? It's probably not 3, right? So we know it's at most 2, right? So I see Andy and Lauren do 1. Jenny's still like on the fence a little bit, and that's okay. So I would say that this needs just one dimension, or this is one dimension. And the reason why is like, if we can imagine we knew what the line equation here, in this case, we actually do know what it is, 3x plus 1. All we really need to know is saying, where is it on this line right here? You can also kind of think about it like, well, if we just like adjusted it and like turned it sideways, it's just like the it's just like this guy right here, where y equals 1. Okay. So you can say that this is really a one-dimensional description. As like we could just figure out what this line is. We could say, where are we on this diagonal line? All right. This is a little fun. So now we have something similar. If we say this is one-dimensional, how many dimensions this is? So you can see here, it's more or less a straight line, but there's also a little bit of like noise, a little bit of fluctuation. How many dimensions would you say this is? I see Lauren do 1. Anyone else got a guess? See Jenny do 2. Oh, good. We got some controversy here, right? So I would love to hear a little defense, right? So Lauren, why choose 1?
Because I guess like I don't know. I'm looking at the y equation and it's just based off of x, and then there's like some noise. So I don't know if the noise is like, maybe the noise is its own dimension, actually, like thinking out loud,
Okay.
but it's definitely not based off of y, I think.
Mm-hmm. Yeah. So you're saying like there's definitely like it's kind of similar to this one right here, where essentially if we had a single line, we could describe it, right? So like that's kind of like the reasoning going through here. We have a single line, right?
Yeah,
More or less.
well, I guess it's like, yeah, exactly. And I guess I think of it as it's still based off of x, and it's just like inputting kind of a discrete tweak to.
Oh, okay. So like saying how far off it is from this. Good. Yeah. Okay, cool. So they're definitely, I think most people would agree is that it's more or less on this one-dimensional line, right? And then Jenny, I'm going to have you be able to say it too. Why do you say 2 dimensions?
Yeah, I think the same thing as Lauren. It's just for me, it results in a different result. So yeah, I was thinking if the one above is 1 dimension, then the one below adds noise to that. But I also get Lauren's idea that that y equals x could be like our default situation. You know, in the universe where y equals x, we have this 1 dimension, which is the noise. But so yeah, I guess I say 2 because the previous one was 1, and to me this looks like taking the previous one and adding a dimension to it. But I get Lauren's point of view too.
Yeah, and I would say there's a lot of argument you could go towards this. Some people could say, you know, really with this noise, you can say it's 1 dimension. Essentially, it's like the y equals x, and there's some noise, but it's so unimportant, you know, it's not considered. You can also argue in the same way with Jenny saying, you know, like it's more or less on this y equals x part, and we need that kind of like, you know, where we are on that line. But there's also like this other dimension of saying essentially, you know, how much noise we have. And so I would say, depending how you look on it, you can think of this as 1-dimensional or 2-dimensional. To describe it directly, you would have to have essentially 2 numbers. Note that it's a little different from us saying like, you know, in the random noise, we basically need to know this axis, this x-axis and this y-axis. We can instead say, okay, we have this y equals x line. Where are we on this y equals x line? And then say how far up or above, or sorry, above or below we are from this y equals x line. That would be like the 2nd dimension. And this actually what brings us into like PCA and everything, is that we have something where certain axes are more important, essentially. We actually count it by variance, but basically you can probably guess is that this dimension is probably gonna give a lot more information than saying how much, you know, quote unquote noise we are from this line. So that's actually a really important aspect that we can say, oh, some axes are more important than others. Cool, thank you guys both for sharing. All right, and the last one, this one's just a fun one I just like to throw. What dimension is this thing? I'll give you a hint, it's definitely not 3. Or maybe, no. So I see Lauren do 2, Jenny do 2. Andy's like, I'm just gonna wait for the answer, what Victor says. Yeah, and this is where I would actually say it is 2 dimensions in this way. There's a lot of like, I think you could debate either way in this way. And the real reason why we'll say it's 2 dimensions because PCA really only does shifts in rotation, so we can rotate the line or kind of move it back and forth. It doesn't like or move it up and down. There's no way to really rotate or shift this up and down to make it into a single line. Like you essentially will always have to have 2 dimensions. It technically can be made into 1 dimension, something called a parametric fit, but that's not something that PCA does. So for example, if you imagine like you describe this function right here, which is actually this function right here, and just say where you are in time, essentially like if you imagine traveling along like this route and say where you are, you could technically say it's 1 dimensional, but for PCA's sake, we'll call it 2D. Okay, cool. All right, but also what's kind of fun about this, you can also imagine the main information, if you imagine 2 straight lines, you can actually say, hey, well, there's a kind of a, oops, there's a single line that kind of goes in this direction. Oops, it's supposed to be straight. And then you can say how far you are off of that line too, kind of similar with the noise direct description here. So you can definitely see there's definitely a lot more information in one direction. We can more or less get it right by just saying this y equals x looking, you know, line right here. And then say the extra dimensions, like how much, you know, are you off from that line? Okay.